Assalamu alaikum. My name is RAKIBUL HASAN and today I will be presenting a foundational topic in sequential digital logic, the clocked RS flip-flop and JK flip-flop. These two circuits are critical building blocks in memory storage and timing-based applications, and mastering their behavior is essential for designing reliable digital systems. Over the next few slides, we will explore how they work, their advantages and limitations, and where they fit in real-world design. To begin, let's quickly revisit where flip-flops fit in the bigger picture of digital systems. In digital logic, we deal with two main types of circuits, combinational and sequential. While combinational circuits produce outputs based only on current inputs, sequential circuits take it one step further. They also depend on fast states. That's where memory comes in. Sequential logic circuits can store information and they transition between states based on a synchronizing clock signal. This enables more complex behavior like counting, storing bits, or defining a specific operation sequence. Flip-flops are the most fundamental memory elements in this realm. Today, we will look closely at two of them, the clocked RS flip-flop, which introduces the idea of getting inputs with a clock, and the JK flip-flop, which builds upon that concept to solve certain design issues. Understanding these building blocks is essential for designing anything from simple timers to full-blown CPUs. Now that we understand the rule of sequential logic, let's zoom in on one of its most important elements, the flip-flop. A flip-flop is a basic memory unit that can store one bit of data, either a 0 or a 1. What makes flip-flops unique is that they are bistable, meaning they have two stable states. This allows them to act as memory cells in digital systems. They are controlled by inputs and often a clock signal, which ensures that state changes happen in sync with the rest of the circuit. There are several types of flip-flops like RS, JK, D, and T, each with its own behavior and use cases. Today, we will focus on the RS and JK flip-flops, which are foundational and will help us understand more advanced types later on. Let's start our deep dive with the clocked RS flip-flop. The RS stands for reset and set, which are the two main control inputs. What makes this a clocked version is that the flip-flop responds only when the clock signal is active, so it adds a layer of synchronization to the system. Now, let's take a closer look at how the clocked RS flip-flop actually operates. On the left, we have the logic diagram. You will notice that both the set and reset inputs are gated through the clock signals. This means the flip-flop only reacts when the clock is high, helping ensure stable timed change in output. On the right, we have the truth table, which lays out exactly how the circuit behaves for different combinations of inputs. When the clock is low, the inputs are ignored and the output remains unchanged. When the clock is high, then S is equal to 0, R is equal to 0, the output holds its state, and this is the memory function. S is equal to 1, R is equal to 0, we force the output Q to 1, this is a set operation. When S is equal to 0, R is equal to 1, we force Q to 0 or reset. S is equal to 1, R is equal to 1, this is an invalid state where both inputs try to control the output in opposite ways. This condition leads to unpredictable behavior and should be avoided during circuit design. The flip-flop's ability to hold its state or update it in sync with the clock is what makes it such a powerful component in sequential logic design. Now that we have explored the limitations of the clocked RS flip-flop, especially its undefined condition, Let's move on to a more versatile solution, the JK flip-flop. It was especially designed to overcome the ambiguous state issue we saw in the RS type. Like the RS flip-flop, the JK version also uses two inputs, but instead of S and R, we have J and K. These inputs are similar in function. J is like set and K is like reset, but with a key improvement. When both J and K are active at the same time and the clock is high, the JK flip-flop doesn't go into an invalid state. It toggles. That means it switches its output to the opposite of its current state. This added feature makes the JK flip-flops more reliable and extremely useful, especially in circuits that need counting or toggling behavior. It's a powerful and flexible component in sequential design. Let's now look at how the JK flip-flop works in detail. Just like the RS flip-flop, it has two inputs, J and K, along with a clock signal. But unlike RS, the JK flip-flop eliminates the undefined or invalid state we saw earlier. This truth table on the slide shows how it behaves. When the clock is 0, the flip-flop holds its current state regardless of the J and K inputs. When the clock is 1, J equals 0, K equals 0, no change, the flip-flop maintains its states. When J is equal to 1, K equals 0, the flip-flop sets outputting a logic 1. When J equals 0, K equals 1, the flip-flop resets outputting a logic 0. When J is equal to 1 and K equals 1, this is the special case, it toggles the output. So if U was 0, it becomes 1, and if it was 1, it becomes 0. This toggling ability is extremely useful in applications like counters, where we want the output to flip every time a clock pulse arrives. That's what gives the JK flip-flops its versatility over the basic RS design. Now that we understand how clocked RS and JK flip-flops operate, let's look at where they are used in real-world digital systems. Flip-flops are the foundation of memory and state-based circuits. The clocked RS flip-flop can be found in simple laces or as basic elements in state machines where the system needs to remember certain conditions. However, due to the undefined state issue, it's often used when designers can ensure inputs are controlled precisely. The JK flip-flops, on the other hand, is far more versatile because of its toggling behavior and predictable output. It's widely used in binary counters, frequency dividers, and control units of processors. For example, in a divide by 2 circuit, every clock pulse toggles the output exactly what the JK flip-flop excels at. So either it's storing a bit of data in a register, cycling through state in a sequencer, or building blocks inside a CPU. Flip-flops make modern computing possible. Now let's compare the clocked RS flip-flop and the JK flip-flop side by side. The RS flip-flop is conceptually simpler. It works well in controlled conditions where we can ensure that both inputs aren't high at the same time. Its advantage is in its simplicity. It uses fewer gates and it's easier to understand for basic memory applications. However, that undefined state when both set and reset are high is a significant drawback. The JK flip-flop, on the other hand, was designed especially to fix that issue. It handles all input combinations reliably, and when both J and K are high, it toggles. That makes it much more versatile, especially for circuits like counters or dividers where toggling is required. In summary, RS is simpler but more fragile. JK is more robust and flexible but slightly more complex in design. When choosing between them, it really comes down to what the application demands: clarity and simplicity, or flexibility and power. Before we wrap up, let's quickly look at some key design considerations and potential issues when working with flip-flops. First, we need to be mindful of race conditions. This occurs when signals arrive at different parts of the circuit at slightly different times, possibly causing unintended state changes, especially in feedback loops like the ones in JK flip-flop. Second, age triggering is crucial. Most modern flip-flops respond to changes only on the rising or falling edge of the clock signal. This makes timing more precise, but it also means that setup and hold times must be carefully respected to avoid glitches or metastability. Finally, in actual circuit design, these flip-flops are often implemented using hardware description languages like Verilog or BSDL. Designers simulate and test their behavior digitally before fabrication to catch errors early. So the theory is powerful, but making these circuits reliable in real hardware means paying close attention to timing, feedback, and synchronization. To wrap up, let's summarize what we have explored. We started by understanding the role of flip-flops in sequential logic, how they serve as memory elements in digital systems. We examined the clocked RS flip-flop, which is simple but can enter an invalid state if both inputs are high. Then we looked at the JK flip-flop, which enhanced that design by resolving the undefined condition and even adding a toggling feature. We compared their behaviors, studied how they respond to different input combinations, and explored their real-world applications from basic memory storage to counters and control circuits. The key takeaway is that flip-flops are not just theoretical, they are the backbone of digital devices we use every day. Understanding how to design and use them effectively helps us build systems that are synchronized, reliable, and powerful. Thank you for your attention.